Hi, and welcome to online lecture 26. Today we will be discussing the first part of regression. Okay. Now, just like there are many kinds of correlation, there are many kinds of regression, but we are going to focus on one specific kind called simple linear regression. So the good news about this topic is that correlation and regression are very, very similar. We still have two continuous variables. We're still focused on relationships and associations, and they even have very similar assumptions. So what's the difference? Well, whereas correlation gives us the direction and strength of a relationship, regression takes us one step further. It allows us to predict one variable from the other. It allows us to predict one variable from the other. So how? First, you label one variable as independent X and one variable as dependent Y. Then you find a straight line through the data that provides the best fit for that data. That's called the best fit line. And then you find the equation for that line. Okay, so we already had talked about with correlation, we were looking for a linear relationship. Same thing for regression. For that simple linear regression, we're going to look for a linear relationship. So no surprise that we are looking for a straight line that provides the best fit for the data. So let's look at a couple of perfect correlation examples. And we see on the left here, we have r equals 1. The line goes through all of the points. Perfect. And on the right, we have r equals 1. The line goes through all of the points, and it's perfect. But you can also see that even under these perfect circumstances, a correlation is not enough for prediction, right? Because this one is almost a straight 45-degree angle. So we would probably predict that if a person has a score of 4 on the x-axis, they'd have a score of 4 on the y-axis. Whereas over here, it's not quite the same angle. So here, maybe a person who has a 4 on an x-axis only has a 3 on the y-axis. So even though they're both perfect, they would give you different answers in terms of prediction. So correlation's just not enough for prediction. We need that regression. So now I'm going to show you this scatter plot, and I'd like you to think about where is the best fit line through this? Where is the best fit line through this? Just imagine a straight line that goes through this data that fits as many of the as much of the points as possible. Here's that same scatter plot with some different lines through it. I'm guessing most of you probably chose rule 4, this line here that goes through 3 of the points. And if you did, you would be absolutely correct. That is the best fit line for this data. And I'll show you in SPSS how they found the best fit line for this data, how the program did, I should say. And you can see it goes through those 3 points just like the example did. Okay. Now I want you to look at this data set, this scatter plot. And I want you to do the same exercise. I want you to imagine the line that best fits this data. Imagine the line that best fits this data. Here it is. That's the line that best fits this data. So whereas the first line was indicating a positive relationship, this line's indicating that negative relationship, right? Because it's going from upper left to lower right. As x increases, y decreases. So that's interesting, but perhaps the even more interesting thing about this is that this best fit line goes through none of our data points. Did you catch that? This best fit line goes through none of our data points. So it's really not about hitting the most data points, it's about minimizing the distances between the points and the line. Let me say that again. You're trying to minimize the distances between the points and the line. Okay. So let's talk a little bit more about this notion of best fit line and prediction. So the data points all come from our sample, right? That's our data. We want to use our sample data to make predictions about the population. So we use the best fit line. In other words, for any independent variable x, we use the line to determine what our predicted dependent variable will be. So whenever we choose any x we want, how do we figure out the y? The line, not the points, the line. Okay. And that best fit line is also called the regression line. That best fit line is also called the regression line. So here we go again, showing you the best fit line through that set of data. And we observed that, yeah, in reality, it probably is minimizing these vertical distances between the point and the line. And we also observed that, again, if we want to make a prediction, if we want to look at someone with forward exposures, we don't go up to this point, we go up to the line, and that's what we would predict. That value right on the line, which is probably right around 6. Okay. So let's talk a little bit about how we find the best fit line. Now I have some more good news for you. You're actually never going to have to find the best fit line. We're going to let SPSS do that for us. But I do want you to understand the process. So we're going to talk about the process a little bit. So mathematically determine the solution where the distance between y, our y dots, our sample data, and our y hat, our predicted y, our line, is the smallest for all data points. This vertical distance between the data point and the line represents the error. Some distances will be positive, some will be negative. So all of these values are squared to obtain positive values. You remember way back when we were calculating variance and we had to square all those values because otherwise, if you add them all up, you get 0. Same story here. If we added up all those positive and negative values, we'd get 0. So we square them all to obtain positive values. And this is called finding the least squares error. This is called finding the least squares error. Okay, so let's take a look at this a little bit more. And I like this diagram. I think it does a nice job of showing this, of the least squares error. So here is our happy data point, xy. Here is what we would predict it to be on the line. This point is still our same x, but it's y hat. Because it's our predicted y. Sorry, right here, our predicted y. So this distance of y minus y hat is our error. So again, this distance between our y and our y hat is our error. Okay. So now let's talk through the assumptions of simple linear regression. And as I promised, they are very similar to correlation. Not the same, but similar. First of all, the individual cases or persons have to be independent of each other. Okay, same as correlation. The variables must be linearly related. Same as correlation. Remember, they have to be, the relationship has to be along a line. Now, the truth is there are a lot more assumptions for simple linear regression, and they all kind of relate to the errors. But I'd rather not burden you with going into all of that. If you're interested, contact me. We can talk about it. But I'm just going to say the errors have certain characteristics that make them nice enough. All right. So now we're up to the one equation that you are going to use in regression. Excuse me. And that's the equation for the best fit or regression line. So remember, the regression line will be given to you, but you have to use that line to do some prediction. So the equation for the regression line is used for prediction. We have our y hat, what we're trying to predict for y, equals bx plus a. Now this may actually look familiar to you. You may have seen an equation way back when in some other course, math course, where it was y equals mx plus b. Now this is actually quite similar. So let's talk this through. Basically, we have an intercept and a slope. B, the one next to the x, is the slope, and A, the one by itself, is the intercept. Now the intercept is the predicted value of y when x is 0. So even when x is 0, even when the independent variable is 0, what's y? That's the intercept. The slope is how much y is predicted to change as x changes. For every 1 unit change in x, how much does y change? X is our score of x, and y hat, remember, is our predicted score of y, our y on the line. And if you recall, the goal of the regression line is to minimize those differences between predicted and actual values of y. Okay. So here is that least squares error again. And you can see now, we'll look at this actual formula here, y hat equals bx plus a. And we would be given what this line actually is, what the formula is. And then we could fill in our x and get our y hat. So we're given the b, we're given the a. We choose an x. It could be all the way over here, 1, or it could be to the right, maybe a 5 or a 6 or a 9. And then we can figure out what our y hat is. And remember again that these vertical distances, the vertical distances are our errors. The distance between y, the point, and y hat, the line, is our error. And each point has some error in this example. What if you had a point exactly on the line? No error for that point. No error for that point. So for a perfect relationship where all the dots are exactly on the line, you'd have no error. Okay. Let's look at an example. Wagner, Compass, and Howell back in 1988 investigated the relationship between stress, measured in terms of negative life events, and mental health in first-year college students. They used a negative life event scale called the Hopkins Symptom Checklist 50 to assess the presence of 50 psychological symptoms. Each symptom was rated on a 1 to 4 scale, with higher ratings indicating more symptoms. The researchers believed that students who experience more negative life events will in turn have more mental health symptoms. We wish to be able to predict mental health symptoms based on stress or negative life events. And I write here on the bottom that the IV is negative life events and the DV is mental health. Okay. So, important point here, we can actually still, just like with correlation, we can have one-tailed or two-tailed relationships here. And in this particular example, it looks like we have a one-tailed because we're saying more negative life events, more mental health symptoms. We're telling you the direction. In other words, we're making it one-tailed. If I had said instead, the researchers believe that students will have, researchers believe that there will be an association in students between negative life events and mental health symptoms. If I just said that, it wouldn't tell you anything. It wouldn't tell you that it was one-tailed. It would be two-tailed because it's not giving you direction. In this case, you have direction. Okay. So let's continue talking about this. Okay, so we're given a little more information. Even with 0 life events, the predicted Hopkins symptom checklist score is 73.5. For every increase in score by 1 for negative life events, the predicted HSCL score increases by 0.8. So if someone has a score of 10 on negative life events, what's their predicted HSCL score? Okay, so now we get to use the equation for the line to figure out someone's predicted Y based on 10 negative life events. Okay. So the first thing we got to do is figure out what this formula is, right? So that means we have to figure out what the A is and what the B is. Okay, because we're given A and we're given B and we're also given X. So we have to figure out all 3 of those actually. Okay, so what's the intercept? What's the one that goes along with the 0? It's the 73.5. That's our A. And what you're doing is you're looking for the one that's paired with the 0 for the X. What is Y? 73.5. That's our A. Now we're looking for our slope. How does that go? We're looking for the one that's paired with, for every increase or every decrease in score by 1 for X, what does Y do? That's this one. That's our slope. That's 0.80. Because for every change in score by 1 for X, the predicted HSCL score increases by Y. Okay, so that's 0.8. If someone has a score of 10 on negative life events, what's their predicted HSCL score? That's simply our X. That's what we're asking about. 10 on negative life events, 10 on X. Okay. So here's our equation again. Y hat equals BX plus A. I think we've done a nice job of filling in. For B, we have 0.8. For A, we have 73.5. And for X, we have 10. So I would say the hardest part about one of these problems is not really doing the arithmetic here, but actually figuring out which piece goes where. That's why I'm trying to give you as many hints as possible. Because once we have this, we just multiply and add. So 0.8 times 10 gives you 8 plus 73.5, and then Y hat equals 81.5. Now I want to make a couple of quick points. Let's talk about this line here. What if I had said for every increase in score by 1 for negative events, the predicted HSCL score decreases by 0.8? What would that do? Then you would just make this negative 0.8, negative 0.8. And then we would have taken negative 8 plus 73.5. Okay. All right. So now we've talked a lot about the comparison of correlation and regression. Let's do it formally. There's only two important differences here, and I'll show you what those are. Not up here, not till you get all the way down here. So the two important differences are the independent and dependent variables are defined for simple linear regression. Remember, for Pearson correlation, that was the only case, the only situation where the independent and dependent variables are not defined. That was the only test we'll talk about where that's the case. Now, the purpose is important too. On the left, with Pearson correlation, we say it's association. On the right, we say it's association and prediction. True. Now, here's the thing. When you get a word problem that deals with correlation or deals with simple linear regression, it's probably not going to say, well, the IV is this and the DV is that, right? So what you're going to rely on in differentiating between correlation and regression is the wording. So let me give you the trick. If it just says that something is associated with something else or something is related to something else, it's correlation. If it says this thing predicts something else or is predicting or predicted, some form of predict, then it's simple linear regression. So bottom line, you are looking for some form of the word predict. If you see it, it's simple linear regression. If we're just talking about association or relation, it's Pearson correlation. Okay. Now, what's interesting here, why am I showing you this slide? Because, oops, sorry. Just stopped sharing, I think. Okay, here we go. Why am I showing you this slide? Because in both cases, we have the same line for the set of points. Y hat equals 2x minus 1. Okay, so y hat, our predicted y, equals 2, that's our slope, minus 1, that's our intercept. Our intercept is negative 1. Okay, so we could have said plus a negative 1 here too, if that fits a little better for you. Okay, but the point that I'm trying to raise is that notice how all of these points are on the line. Notice in this case how almost none of the points are really directly on the line. Yet it has the same prediction equation. So what this tells us a couple things. First of all, prediction equation is not enough. It's helpful, but it's not enough. And second, SPSS is always going to give you a prediction equation. You could have a big old blob of dots that means nothing, and it will give you a prediction equation. It'll put a line through them. So we have to have a way to evaluate whether our regression line is a meaningful representation of our points, of our data. Okay. So that's something we'll talk more about next time. Okay. I want to say one other thing before I push on to this last point. So the only test that cannot have a one-tailed relationship, or we're not going to deal with, I should say, one-tailed relationships in this class, are the ANOVA tests. For correlation, for regression, for our Z and T tests, we could have one tail or two tail. Okay, so I just want to make that point clear. All right, so now let's talk about issues with simple linear regression. In fact, I'd love to talk about all the issues with simple linear regression. We're just going to talk about one right now. Okay, we'll talk about the more next time. But here's the one I just want to point out for you. Nonlinear relationships cannot be interpreted. So check this out, this nonlinear correlation, right? Or nonlinear regression, or whatever you want to call it. It's a nonlinear relationship, right? It's not a line, it's a curve. So this is the same issue we had with correlation. So I'm going to say it again, that if you see a curve of dots, a smiley face or this rainbow thing or anything like that, you cannot interpret it using any of the tools that we have. We have no tests to interpret this. Are there tests out there? Yes. Do we have any? No. So none of the tests we have can be used to interpret this relationship. We'll talk about more issues with simple linear regression next time. But for now, that's the end of materials for exam 3. So we'll start fresh with part 2 of linear regression next time, and then we'll go on to chi-square. Those will be the last couple of topics we talk about in this class. And this is your second to last quiz. You go to D2L, go to quizzes, go to quiz 11. The password is 9735, and please answer 2 multiple choice questions. All right, that's all I have for you for today. So stay safe, be well. I'll talk to you next time.